further ado, I'd like to introduce Matt Hatton from Transforma Insights. Matt, welcome.
Thank you, James. I was just checking on my other monitor that I was here, and can you hear me?
You are here. It's not a figment of my imagination, and I can most definitely hear you, sir. So have a great presentation. Thank you for joining us, and I'll see you a bit later. Bye.
Absolutely. James has taken upon himself the unenviable task of defining digital transformation in that little introduction, something which we've also tried to do at Transforma Insights, and it essentially boils down, I think, to a whole set of disruptive technologies which will change over time and which will allow organizations to adapt how they operate to effectively become more competitive. I sometimes refer to some of these technologies as the competitive differentiators of the 21st century. The biggest one of those is probably IoT. AI comes in a close second, and there's a set of other technologies behind the scenes. But essentially, IoT, which is our big bag at Transforma Insights, is the one that we think has the most substantial impact. So a little bit of an introduction on me and the company. So we're a research consulting firm focused on digital transformation, specifically a lot on IoT, and within that, a lot on the telecommunications space, on how you connect all of these billions of connected things. And what I want to talk about today is some key trends in IoT. Well, actually, it's really one key trend in IoT that's masquerading as many different trends. So let's skip on through first to the first slide. If I can get that to move, hang on a second. There we go. Here we are. We're in business. Last year, we at Transform Insights published a report that we were talking about something called the thin IoT stack. Okay, if you hadn't had a chance to look at that, we've got some blog posts on the website looking at it. But the point about that is we've seen the arrival of a set of technologies across IoT, in fact, the whole IoT stack, that are specifically aimed at coping with and dealing with the constraints of things like power, location, space, processing, and several other things that will be increasingly common in a large volume of IoT deployments. You know, there's nothing new in IoT. We've seen people monitoring, well, Coke machines is one, but we've had SCADA systems monitoring smart grids and industrial control systems for many decades. But as we go from the maybe tens of thousands, hundreds of thousands, millions of devices that are connected in terms of very valuable assets, where it's well worth spending a lot of money on keeping tabs on your wind turbine or your heavy piece of industrial kit, we move to the world of billions of devices, where a lot of these things are actually put out in the field for decades, maybe, without wanting to replace a battery, and have very tight constraints in terms of processing and power and all of these various elements, just because you need to keep the cost down, and you may not have access to the various technologies. So our perspective is the shift to this thin IoT stack, to this need to cope with the constraints that I've talked about, is going to be incredibly wide, and it's going to have implications across the whole of IoT and how IoT is deployed. So what I'm going to talk about today is a range of these ways in which it's going to be felt, and therefore the implications it has for the wider market. I mentioned about the thin IoT stack. I'm not going to talk about this one too much, but essentially this is how we see that stack. So it's everything from hardware, the software that runs on that hardware, operating systems and so on. It's networking technologies. It's the middleware for actually connecting and managing the devices. It's edge computing and machine learning, but in a very different way, coping with constraints. And I'll talk about all of these as we go through the session. First things first, this is the mobile ecosystem forum. So I thought the first thing I ought to pick out really was looking at wide area connectivity. And that, probably above everything else, is increasingly defined by the arrival of a set of technologies which are designed explicitly to overcome the constraints, particularly of battery life. So we've seen the arrival of these low power wide area, LPWA, sometimes referred to as LPWAN technologies, where their raison d'etre is to operate where there are constraints of availability of power. And as you can see from the chart, we're seeing significant growth in that space in terms of shipments. So what I'm showing here is annual shipments of devices. The orange is the traditional cellular, 2G, 3G, 4G, 5G. The green is the licensed low power wide area. So that's what is being put under the umbrella of 5G MMTC. So that's NB-IoT and LTE-M today, and there will be some evolutions to that in future, no doubt. And then we have the unlicensed low power wide area. So things like LoRaWAN, potentially Sigfox, depending on how things go with that. But overall, these low power wide area technologies will account for almost 2/3 of new devices shipped by 2030. Now, it's a relatively high rate even today, but a large proportion of that is focused on China. So really, as we see the majority of those devices today shipped in China, but that will evolve over time to encompass much more of the world. There's also a lot of hype around low Earth orbit LEO satellites and their ability to address IoT as another potential to cope with another constraint, not being anywhere near where you can connect to a cellular network. Lots of high-profile announcements, several partial constellation launches, but not a huge amount of customers at the moment. We're expecting quite a shakeout in that space, but it's certainly an interesting one to keep an eye on. There is probably, we think, only a small number of use cases where it will be very valuable, but for the vast majority of use cases, we'd expect still cellular will be the chosen technology. It's just that bit cheaper to deploy and easier to deploy and well within the remit of everybody who's running those networks. So that's the wide area space, but it's not like local area network isn't also getting in on the act of coping with these constraints, or using or providing a set of capabilities which make device manufacturers much better able to produce devices that run on low battery power, or that have high latency for being able to address some use cases which might not historically been able to be dealt with by the likes of Wi-Fi. So historically, Wi-Fi was the dominant option, at least for domestic connectivity. In industrial settings, you might have Zigbee or wireless HART, a bunch of other technologies. But we expect that Thread will become an increasingly important part of the market, particularly off the back of the standardization of the Matter smart home interoperability protocol. So I've illustrated this with the protocol stack for the various bits of what Thread and Matter can do. I could spend hours on this specific subject, but I'm not going to, other than to say that anyone who's not already working with Thread or Matter or exploring those technologies really ought to think about it and ought to move quickly to do so. The advantages associated with those is much more robust meshing, much better ability to have long battery life, lower latency. So as well as those low power wide area, we're starting to see some almost low power local area technologies. I won't refer to them as that because there's a whole bunch of other technologies which effectively have that similar sort of profile as well. But these are certainly some technologies to be aware of. Choice of protocols will also be affected by the constraints on IoT deployment. So I mentioned about Thread and Matter. That was just a couple of examples to throw in, but there's a whole lot of other areas across this whole IoT stack. I talked about the thin IoT stack, which was kind of our perspective on it, but this is a more traditional 7-layer stack. And if we focus in on the network and transport layers, there's a whole lot of choices and adaptations that need to be made in order to cope with this constrained environment. So, for instance, at the transport layer, most protocols are going to choose, or most deployments are going to choose between TCP, Transmission Control Protocol, and UDP, User Datagram Protocol, both of which are part of the IP standard. TCP is more complex. It's a connection-oriented protocol, meaning that it seeks to establish a two-way communication with the receiver. Delivers data data packets in the correct order, resends lost packets, and so on. Now, UDP, in contrast, is connectionless, meaning that it's simply going to send the data packets without really any consideration of whether the recipient's ready, won't seek to confirm receipt, won't retransmit lost packets. Now, as a result, UDP is a significantly lighter protocol, therefore more applicable for constrained IoT. Now, then riding on top of these protocols are two messaging protocols. They're MQTT and CoAP. You may hear reference to those when talking about IoT. Both were designed to make more efficient use of network resources, particularly in constrained environments. So CoAP is constrained application protocol, in fact. And that CoAP is inherently more appropriate for these constrained environments. It's based on UDP, whereas MQTT is based on TCP. But MQTT is more secure and gives more of a guarantee on delivery, but it's inherently a chattier protocol. And the point here is that the choice between these technologies will have implications for how well the application functions, latency, and cost might pan out. Cost, for instance, more bits and bytes of data that are being sent over a network, the more expensive more you're going to pay for connectivity. But it will also impact on choice of which technologies you might use. Are the low power wide area network technologies I spoke about earlier suitable for these applications? And there's a couple of other implications as well. And those relate to security and the cloud. Okay, so I'm conscious I'm getting a little bit deep in the weeds on protocols, but I'll haul it back to a wider view on how the IoT market pans out. But this is quite important. Constrained IoT deployments will predominantly rely on CoAP and UDP. But that has a lot more limited set of security capabilities than the TCP-based deployments. Now, this creates a bit of a challenge for delivering to the cloud. And specifically, it drives the requirement for what we term cloud connectors. And I'll explain why. So the likes of AWS and Microsoft Azure won't accept what's termed DTLS-based security, so datagram transport level layer security, meaning that constrained IoT devices, i.e. the majority of IoT devices in future, will need some sort of protocol conversion for them to be delivered to the cloud. If you're using LTE and 5G, you can just use the hyperscaler's own SDKs for delivering that data into the cloud. Now, the point is, as more and more IoT applications move into the cloud, which they are, it's not the majority today, almost certainly, but more and more organizations are actually basing their IoT deployments in the cloud. This need for cloud connectors or some form of protocol conversion only increases. So the solution is a cloud connector. It's an area we've been looking at in quite some detail at Transforma Insights recently, and the aim of that is to handle secure delivery to a network element and then protocol conversion to then deliver to the cloud. Some vendors have got this capability. Some platform vendors, so Ericsson within its IoT accelerator has a Cloud Connect function. There's operators like Emnify, Telefonica, Verizon have built some equivalent necessary functionality to support it. And for those enterprises that are deploying IoT using these low power technologies and wanting to use the cloud, an awareness of having to do this integration, having to have this capability is a pretty important thing. Now, there's another aspect to this, which I'm going to touch on very, very briefly. For the less constrained devices, there's also a lot more options here now as well in terms of layering on additional levels of security. For instance, the GSMA IoT Safe program provides for a higher level of security baked into the device and potentially controlled by the enterprise. So having gone from a situation of thinking, well, mobile networks are inherently secure and therefore everybody's happy with how that security is likely to play out. Actually, it's become rather more of a complex world with having to cope with these constrained protocols and also trying to layer on some additional root of trust capabilities as per the IoT Safe program. So I guess the takeaway here is that the security requirements are also evolving as we go. Device management. Now, device management is another area where this concept of constrained IoT becomes increasingly an issue. Now, we tend to think of device management as being a pretty done deal. I guess everybody has a pretty good idea of how it works. And with unlimited bandwidth, it's absolutely fine. You can rely on a whole set of proprietary device management protocols based on MQTT, or even some very heavy protocols like TR-069 to handle those firmware upgrades and so forth. But in constrained environments, there's a much greater requirement for a thin device management protocol. And the one that's bubbling up, well, more than bubbling up, it's the default and the generally accepted option is lightweight M2M, the clear candidate here. And while a lot of devices today might feature some rudimentary variant of lightweight M2M, it's in terms of real adoption, it's been pretty limited, but we do expect this to grow quite rapidly. There have been a number of initiatives from, for instance, utilities, from smart meters to include full functioning lightweight M2M in deployments, and therefore we can see a growing demand for this. And one of the things we're working on at the moment is actually forecasting that, looking at how widely adopted this lightweight M2M approach might be. And I mentioned about edge and artificial intelligence when I talked about the thin IoT stack, and it's an increasingly critical part of what we talk about in IoT. For the simple reason that effectively when you start with IoT, you start with remote monitoring, then you go to remote management potentially, and then beyond that is some form of automation. And the requirement therefore shifts to potentially putting more and more of the processing onto the edge device to be able to adapt in real time. Think about autonomous driving. Okay, people talk about autonomous driving as an IoT use case, but the reality is that thing has to operate autonomously. Therefore, you need to put a lot of compute power and a lot of probably AI onto the edge device, i.e. the car, to be able to deal with that. So that trend of putting more intelligence and more potentially AI machine learning onto the edge device is a prevailing trend in IoT. The constraint here is not necessarily the fact of the device itself, but it's the fact that accessing compute resources in the cloud is going to slow down significantly the overall processing time, meaning that the compute capabilities need to be placed on the edge device. So these devices are more constrained in terms of their ability to access the cloud rather than necessarily constrained in battery or other things. So the implication of this is typically when we talk about constrained devices, we're thinking about dumber terminals, right? Things that have less processing, that can send and receive an awful lot less data. But this aspect of IoT actually makes for, or this aspect of constrained IoT actually makes for smarter rather than dumber terminals. You need to put more intelligence, more processing at the edge device, and cope with that as a scenario, just because the relative latency of sending and receiving data back to a cloud data center versus processing on the edge device is quite significant. Now, we ought to mention the dreaded 5G at some point. It should be noted that in the context of edge computing and AI, 5G actually helps significantly with overcoming some of those latency and bandwidth limitations. So, circumstances where the use case justifies the additional hardware cost, 5G is pretty expensive, and probably additional connectivity cost because you might need to send and receive much more data over the network. 5G might actually make sense. The latency challenges associated with communicating back to a central server is suddenly mitigated quite significantly, meaning actually you can do more without putting the edge processing onto the device in a strange kind of way. So 5G potentially changes the way you might architect a solution, mitigating the need for that edge compute and AI on the edge device. Potentially, the autonomous vehicles example, I think, still doesn't apply because you're still going to have not spots, you're still going to have challenges with connectivity, and therefore you still need that device to be able to act accordingly with its own AI capability and its own compute capability. But for rather less life critical applications, shall we say, it may be possible to do it. And indeed, where you've got more control over the environment in which the device is deployed. So a factory, for instance, you may well see more, or we're seeing obviously a big interest in the concept of mobile private networks. Private wireless is coming through quite a lot because of that additional capability to do more with these ultra low latency technology. It also helps to stimulate another form of edge computing, and that's mobile edge computing, MEC. You may well have heard a lot about MEC, putting greater processing at the edge of the network. Increasingly, the latency challenge with communicating over a 5G network or over a cellular network is less about the last mile, less about the cellular element of it, and more about just the distance to the data center, just because of the ultra low latency of 5G. So there's a stimulus there to put the intelligence of the IoT application, the AI or whatever it is, at the edge of the network, which allows for some degree of aggregations and easier management rather than putting it on the edge device itself. So actually that might be the optimal place for locating the artificial intelligence, locating the processing of the application, put it at the edge of the network. Now, today, that's actually not where most MEC is focused. It's mostly focused on operator data centers, but increasingly we should see that move further and further out to the edge of the network over time. Operating systems is another one that has significant implications if you are trying to operate a device at the lowest possible battery consumption, or make it as cheap as you possibly can. We're all aware, of course, of the very small amounts of processing power required by the Apollo 11 moon landing, 32K of RAM and 72K of ROM, which is creepily similar to the levels of capabilities that are envisaged for IoT devices that run operating systems. There's a whole set of of new OSs that have been deployed in IoT, which have similar sorts of capabilities to that actually. But the point being, these things like Amazon FreeRTOS, Riot, TinyOS, and so on have very small footprints on the device, meaning that you can minimize data processing and pretty much anything related to running the application or device, and that reduces the cost and the power consumption and so on. So another layer of that thin IoT stack, which has been evolved to better address IoT. The final element, and some might say the most critical of any IoT solution, is the application. What I'm illustrating here is actually Transforma Insights market forecast, application segmentation into dozens of different use cases, and actually there's hundreds of sub use cases, applications that sit under each of these. So we've identified 200, 300 different use cases, and so the point being, IoT is highly diverse, and there is clearly an overwhelming need to adapt the application to suit the constraints in which it's being deployed. So, for instance, having a highly chatty application is going to cause havoc for low power devices. There have been some stories about smart meter deployments that haven't been able to cope with the protocols that have been used, the connectivity protocols that have been used to deploy them, and making the whole system fall down. So you really need to think about the underlying other elements of the stack when you're provisioning your applications. So, for instance, I talked about satellites a little bit. Today, if you want to use a LoRaWAN over satellite solution, it's essentially a store and forward system. You might get latency to the tune of hours, which might be fine for a simple metering or monitoring device, but for anything that requires more immediate attention, it's obviously not going to be appropriate. Which brings me on to probably the most important aspect of this. There's a huge requirement for all of these constituent elements of the application, and I use the term in its broadest sense, to be optimized with each other. And that includes hardware, which is a subject I've not really touched on an awful lot during this session. In fact, not really at all. It includes also the connectivity I talked about, protocols, device management, data processing, network, the actual application itself to check that it's working within the parameters that are acceptable for the other elements that are being deployed. So the priority for anyone building an IoT application is to ensure that all these elements are optimized to work together. Now, easier said than done. And it does point quite clearly to a much greater requirement in future for the supply of these aspects to be done in a coordinated way. Historically, somebody would buy a device, buy connectivity, build their application without really very much thought for how those things operated together. Now, having to have somebody giving greater consideration to that coordination might mean there's a lot more of IoT building that's drifting towards systems integrators. But most of the mass market of IoT is just not going to be able to afford the associated costs of using a systems integrator for building everything in a customized way. Alternatively, we might see participants in the IoT value chain needing more of a consulting light capability, working on optimizing the solutions with customers, or we might even see a new category of IoT solution vendor arriving. Or vendors need some kind of optimization function which is going to curate a set of interoperable application elements and ensure that they work well with each other. And we've seen a few examples of this. There's Deutsche Telekom's IoT solution optimizer, or there was the recently announced Siemens accelerator platform. This coordination will inevitably help with one of the greatest headaches of deploying IoT as well, fault resolution. You have a lot of disparate elements within IoT that aren't necessarily optimized together, and it's often hard to avoid that blame game between vendors in the event of faults. So optimized solutions should ideally provide that single point of contact. Now, this is the cliched single throat to choke, but it is becoming increasingly important, far more than maybe one-stop shop. People won't buy all of their stuff from one place just because it's more convenient, but if it's optimized, all their elements are optimized together, it does become increasingly important. So we'll see more devices sold with connectivity, more of a requirement for vendors in the space to think about how the clients are deploying their applications and all the various constituent elements. That's about it for me, and I've pretty much run out of time. Just a word on, we run a series of webinars, quick plug for those. Do check out our website for details on those. And with that, I'll just say thank you. I may have a minute remaining for questions, I may not.
You do, well, you technically don't, but I'll give you a minute.
Very kind.
Very quick questions. One from Cedric Morville, a very quick thing. In plain language, how has this well-known chip shortage globally impacted IoT rollouts?
Oh, tremendously. We talk to vendors in the space all the time, and everybody is having challenges with this. So yes, it has slowed down a lot of deployments. There is no escaping that. What you're seeing is companies cannibalizing certain devices to use them for other use cases. There's a famous example of a washing machine manufacturer who was selling their chips onto somebody else because they can make more money out of using them for cars and various other use cases. So yes, it's having a significant and notable impact. Yes.
Fantastic. And very quickly, last question here: chatbots and IoT. So how do you see chatbots being used in IoT? The question actually is related to, does IoT play a role in chatbot conversations across channels? But I've heard that chatbots can be used with IoT to provide information and updates and things like that. Is that something you've seen, or it's very, very rare today?
Well, you think about it. Think about Alexa. All those Amazon devices are IoT devices, and you interact with them, and they can effectively act as a chat bot. Yeah, increasingly important. So we did some work on AI forecasting not so long ago, and the upshot of that was 99% of AI deployments. This is not revenue generating. This is just instances of AI, of which chatbots I would include as one, are on IoT devices. So you think of smart TVs, you think of smart speakers, you think of all these various elements. AI and chatbots is probably is number 2 use case in AI. I think is incredibly important in that space, because that's the way you will interact with a lot of your IoT devices.
Fantastic.
Try to keep that short and sweet.
Perfect. Exactly what we needed. Matt, thank you very much for your insights. That's exactly what MEF is about: interaction, insights, and delivering impact across IoT. That was Matt Hatton from Transforma. Thank you very much.
Thank you.